Right. In the last lecture we had seen the algorithm partial order planning, the POP algorithm. So today we will study two other algorithms, namely GraphPLAN and SATPlan, which have evolved much more recently. So they have evolved in the 90s, and they were actually brought about because planning was being used in a wide variety of practical domains. For example, one of the major breakthroughs in planning was when a complete satellite launch by NASA was done with the help of a planner. So why do we need the planner? Because during the actual launching things can go wrong, things will never go exactly as you want, and so immediately you need an alternative plan. You need to know what is the alternative sequence of actions that has to be taken so that your launch vehicle comes back into the correct path. So that is why and also in a wide variety of other kinds of control applications, planning was being used, and people found that for problem domains which were NP complete or harder, it was being very difficult to use the partial order planning algorithm. So that is why new class of algorithms were born, and these class of algorithms made use of the fact that the more recent computers that we had more amount of space and had more computation power. So we could have algorithms which were infeasible 20 years back, but are perfectly feasible today. So I will talk about two such algorithms in this lecture. To start with, we will look at the GraphPLAN algorithm. So firstly, let us see what is a planning graph. A planning graph will consist of a sequence of levels that correspond to time steps in the plan. So I will divide the planning into sequence of time steps. Each time step or each level contains a set of actions and a set of literals that could be true at that time step depending on the actions taken in previous time steps. So it is like unfolding the possible set of the set of actions and the set of initial facts that we have describe a search problem. So we can unfold it into a state space graph, right. So this is the state space graph which is levelized depending on the distance from the start state. Okay. But we will see that it is not so simple, because there will be conflicting set of events in the graph. For example, if you take this action, then you will not be able to take another action. So if you have achieved this, then you cannot achieve that at the same time. So we will see things like that. And then for every positive and negative literal C, we add a persistence action with precondition C and effect C. I will shortly explain why we need this. This is the no action action, the action which describes that there is no change in C, in the truth of C. So whatever we had as the truth of C in time step k will be the same as the truth of C in time step k plus 1. So in order to achieve that, we need some action which will tell us that action is this persistence action. So it just retains the state of that literal up to the next cycle, and we need to define that, because when we say that whichever things that we are saying will change and the others will remain same in a logical framework, that connotation has to be formally expressed. So that is why we need this persistence action. Okay. So let us look at this example, that the start. So this is the famous question about whether you can have the cake and eat it too, right. So the start is that we have cake, and in the finish we have cake and eaten cake. So we have eaten it and we still have the cake, right. So obviously we require some actions. The first action is eat cake. So I have written down the actions in the scripts format. So the action name is eat cake, the precondition is have cake, effect is eaten cake and not have cake, right, and the other action is bake cake, which has a precondition not have cake and the effect is have cake. Now, let us see how a planning graph for this is going to look like. So, we will start with the step S0. So, initially we are in the step S0. So, in this initial state what we have are the following. We have and we have right. What are the actions that we can have here? Let me enumerate the actions. One is the persistence of this, which means that I will just retain this. If I retain this, then I will have, let me so this is the persistence action which says that just let us keep the cake for the next time step, right. An alternative action is eat cake. See, at this, in this time step, bake cake is not a possible action because bake cake has the precondition not have cake, but since we have cake, so we cannot use that. So, if we apply the action eat cake, then this is going to produce two effects. We will have not have cake and we have eaten cake. Okay. The third action is the persistence of not eaten cake. If we use that action, then we will have not of eaten cake. Right. So, this is what we have in the step S1. So, this describes all possible things that we could have in the state S1 in the next time step, but note that we cannot have all of them because some of them are conflicting with each other. So, let me note down what conflicts with each other. So, have cake and not have cake, obviously they conflict. So, I cannot have the two of them. Similarly, eaten cake and not eaten cake cannot be there together, right. There is also the case that have cake and eaten cake have a conflict. Why do they conflict? No.
But even after baking cake, you still have eaten cake.
No. Okay. Let us see. These two actions, this persistence of this and this, these two actions are mutually exclusive actions. Why? Because one produces have cake as the result, the other produces not have cake as the result, right. This is one reason why these two are exclusive. They are also exclusive for another reason. The reason is that the effect of eat cake negates the precondition of this action. See, this is going to produce not have cake and then this cannot be applied because you do not have cake anymore. Remember that in partial order planning also we had this problem, right, and that is why we were promoting or demoting anything. But here we want that these two actions both to be applicable in the same time step, which is not possible because we have to either demote or promote one of them. they cannot be serialized in any order. If we put eat cake before the persistence of this, then the eat cake will produce not have cake, and then this action cannot be executed anymore, right. So, the ordering between these is important. So, we cannot have them in the same time step, right. So, that is another reason why there is a conflict between these two. Also, we have a conflict between not have cake and not eaten cake, and the reason is that this is producing again for the same reason, this is producing eaten cake and this is producing not eaten cake, right, and also this is producing eaten cake which negates this one, right. So, in the planning graph what we will do is we will maintain the links between the actions, indicating that which two actions cannot, which pairs of actions are incompatible, yes, which are exclusive, and also we will maintain links between the propositions that are created as the effect of these actions, right. So, some of them can be mutually exclusive like the ones that we have drawn here. So, we will maintain all these links in the planning graph, right. Let us look at one more level of this, what happens after this. So, we have cake, not have cake, eaten cake, and this thing. So, let us apply one more round of the actions. So, now I can also use the bake cake option. So, let us say that I try bake cake, right. So, the precondition of bake cake is not have cake. So, not have cake, and the effect of this is to have cake. Okay. And the persistence actions of have cake is also going to produce the same result. The persistence action of not have cake will produce not have cake, then we can use eat cake here as another action. So, what we are doing is we are applying all possible actions from one level to another. So, this action can also be used because I have cake. So, I can eat cake, and the effect of that is not have cake and eaten cake. And the persistence action of eaten cake is also going to produce this, right, and then we have not eaten cake, and we have this. Yes, it does not do anything, but it tells you that you can, in the next step also you can have cake. See, the use of, suppose you did not use these persistence actions in this level, suppose we did not use the persistence actions, right, then the only action that you can apply is eat cake. So, in the second time step you will not have cake, right, but you may also choose to have cake in the next time step. You can still have cake in the next time step. Not clear? Huh? Okay.
Sir, but then what is the difference between this time step and the next time step?
No, what we are trying to figure out is that in a given time step what is the set of propositions that can be true. What is the set of propositions that can be true? Okay. Now, after time step 1 we found that we have got a bunch of propositions, but there are mutexes between them. If I have this, I cannot have that, right. So, this is a set of propositions which have certain links between them, indicating that which pairs are compatible and which pairs are incompatible. Now, I have a goal in mind. In this case, my goal is have cake and eaten cake, right. But after the first step, you see I have cake, I have eaten cake, but there is a mutex between them. So, my planning problem is not yet solved, right. My planning problem is not yet solved. So, I apply another step of this. On this set, I again apply the set of actions and get a new set of propositions, which is what I get after the at time step S2, right. Yes, 1 minute. So, what we try to check there is that do I now have cake and eaten cake without a mutex. Now, the point is that as you progress through the steps of this algorithm of building the graph, the number of mutexes is going to decrease as you go ahead. And why is that so? Because we are finding out alternative ways of achieving that proposition. In the first time step, I could not produce have cake and eaten cake at the same time, right. But then after baking another cake, so if I eat the cake in the first time step and then bake a cake in the next time step, then I will have cake and eaten cake. Now, to answer your question that why do we need the persistence action? We need the persistence action to maintain that I have already eaten a cake. Otherwise, your eaten cake will not appear here, and then you will not be able to have the cake and have eaten the cake. Understood? If you do not have the persistence of the eaten cake, then in every alternate step you will eat the cake, then do not have a cake, so you will bake one, so you will again have the cake, but you still do not have eaten cake, because if you do not have the persistence, so you will have it like this, then again you will eat cake, in the next cycle you will have eaten cake, but you will have not have cake, right. Could I make myself clear? So, you have to maintain also the persistence actions for those propositions which do not change into the next time step. So, now let us see. So, yes.
How can you apply 2 actions at a time to the same?
We are not applying 2 actions at a time. We are just enumerating all possible actions that I could have taken in that time step. I am just enumerating all those and I am clubbing them together, but I am also maintaining these mutex links which tells me that which pairs are compatible and which pairs are incompatible. So, the planning problem is not solved by creating this graph, but the point is that when I finally have cake and eaten cake in a non-mutex way, then most probably there is a subset of this graph which is the plan, right. And indeed, if you look at this case, then what is that subset of the graph? Let us start from here. The subset of the graph which achieves the desired plan is to first eat cake, right. Then you will have not have cake and you will have eaten cake, right. Then you can bake cake, bake the cake, and then you have cake because of the baked cake, and because of the persistence of not eaten cake, I have eaten cake. So, this one in blue represents the actual plan that I want. So, just unfolding the planning graph is not sufficient, right. But one thing I am certain is that as long as I do not have the goal propositions in a non-mutex way, I know that my plan is not yet complete. Whatever I have seen so far in the plan graph does not contain a plan, right. The moment I find that they are appearing in a mutex way, non-mutex way, then I know that I possibly have a plan, but even then I may not yet have a plan. I may still have to unfold it for a few more cycles, right. Now,
So if there is no mutex, that means there is a plan.
no, okay. This is an interesting thing. Just take this down as an exercise, that after we do all this, I will explain the algorithm etc. in details, but whenever we have the set of goal propositions in a non-mutex fashion, it is a necessary condition to have the plan, but it is not a sufficient condition to have the plan, right. Now, try to get this into your mind and try to figure out a counter example which establishes this result. So, could I make the problem clear? The problem is that I start with the initial set of propositions and the set of actions, and then I am progressively at each time step I am taking my entire set of propositions and applying the set of actions, right, to get the set of propositions for the next time step. In each time step I am maintaining the mutex links between the propositions, right, and then I am continuing this until I reach a point where the set of goal propositions appear in a non-mutex way. So, there is no mutex links between the set of goal propositions. At that point of time, there is a possibility of having a plan in the set of steps that I have unfolded so far, but it is not sufficient. So, try to find an example where it is not sufficient. Okay. But there are some other issues which we also have to understand. We have to understand that is this graph, the planning graph that we are describing like this, is it finite, or could we forever keep on unfolding it, right. Now, note one thing, that if we have a set of propositions as non-mutex in any time step, then they will remain non-mutex for every time step in the future. Why? Because the individual persistence of those propositions will carry them over into the next time steps. So, if at time step k I am able to achieve two propositions without a mutex, then in time steps, all time steps greater than k, I will be able to achieve them without a mutex, and that I can do by just carrying them over through the persistence actions into the next time step, right. So, how are the mutexes going to change? So, anything which we have without a mutex will remain without a mutex forever, but those which currently are with a mutex can become independent in future time steps. So, what we can say is that these mutex links can only disappear as we go ahead, right. Okay. Now, since we are clubbing all the propositions that we could possibly achieve in a time step, so suppose we end up in a scenario where in two successive time steps we have the same set of propositions and the same set of mutex links, then we can say that any future steps will produce the same thing. So, I will have reached what we call a fixed point. So, a fixed point is the core thing here, and we have to realize that a fixed point will always exist for this, and the reason why it will always exist is that these mutexes can only disappear, right, and the set of propositions that we have here is finite. So, the two things that can change over time is new actions can become applicable, new propositions can get generated, and mutex links can disappear, right. But each of these will taper off at the end, because the set of propositions is finite. So, you cannot keep on adding propositions forever, and see that a proposition only appears once in our this thing, because we are maintaining the links between them. So, a proposition does not appear multiple number of times in a single time step. So, we have one half cake, one not half cake, one eaten cake and not eaten cake, but they can be achieved in different ways, right. And the mutex links will also taper off in the end. They are going to reduce, and then after some time they will not reduce anymore. So, that fixed point establishes that this planning graph will have finite depth, right. Now, when we reach the end of the planning graph, and if we find that we still do not have the set of goal propositions in a non-mutex way, then we can say that the plan does not exist. Then we can say that the plan does not exist. Otherwise, a plan may exist and we have to find it out. Now, how do we find out whether there is a valid plan? So, we have to find out whether we are able to achieve this at each step through a set of non-mutex actions, right.
So, at fixed point we stop unfolding.
So, one option is that you unfold the graph right up to the fixed point, and then check whether in the fixed point you are able to find all the goal propositions in a non-mutex way. They are all independently achieved. If that happens, then you start walking backwards from there, trying to pick up actions which are non-mutex in nature, right, and go back right up to the start state to trace out the plan, right. We will see more examples to understand this. So, once we trace out the plan, then we say that this is the plan, fine, but we need not actually unfold the graph right up to the end, because the set of goal propositions may have appeared much earlier than the entire depth of the planning graph, right. So, we can do a kind of iterative deepening, and that is exactly what GraphPLAN will do. So, let us go forward and take a look at this. So, to summarize what we have discussed so far, mutex relation exists between two actions if one action negates the effect of the other, like one is producing half cake and the other is producing not half cake. So, these two actions are obviously mutually exclusive actions. Then interference, one of the effects of one action is the negation of a precondition of the other, right. For example, eat cake produces not half cake, so the persistence of half cake will conflict with this. Anything which requires half cake will conflict with this. The third is competing needs. One of the preconditions of one action is mutually exclusive with a precondition of the other. So, for example, if you look at bake cake and eat cake requires half cake and bake cake requires not half cake. So, they have competing needs. So, they are also mutually exclusive actions. So, these are the three rules which define which actions are inconsistent, which pairs of actions are inconsistent. And then a mutex relation exists between two literals. Literals means the propositions that we have. If one is the negation of the other, like have cake and not have cake. So, previously in the last slide what I discussed was the mutex between the actions, and this is the mutex between the literals. And the second one is each possible pair of actions that could achieve the two literals is mutually exclusive, which means we have inconsistent support. Right. For example, in our example of the cakes, see we have cake here, we have eaten cake here. So, we have both of them, but they have inconsistent support because eat cake can be achieved by this action and have cake can be achieved by this action, and these two actions are mutually exclusive, right. So, we will have cake and eaten cake in the next time step, and then you see that I am having have cake by virtue of baking cake, right, and I will have eaten cake by virtue of eating the cake in the previous time step, right. So, these two actions are non-mutex, they can both take place, right. And why are these two non-mutex? Because these two actions in turn use two preconditions which are not conflicting. So, it used have cake, not have cake, and this used eaten cake, these two were not conflicting, right. So, therefore, I could use these two actions. So, there is no mutex between these two actions and they achieve this have cake and eaten cake. So, there is no mutex between these two again, right, clear, right. Then let us have a look at the function GraphPLAN. So, the graph initially is the initial planning graph of the problem. So, initial planning graph consists of the initial set of literals, and we are given the goals which is a conjunction of literals. Then we do the following. If goals are all non-mutex in the last level of the graph, by last level means that current last level. So, I am unfolding it one step at a time. So, if I find that the goals are all non-mutex in the last level of the graph, then there is a possibility that I have a plan. So, we try to extract solution from the graph. If solution is not failure, which means that if we are able to find the solution, then we return solution. Right. I have not yet explained what is there inside this extract solution, but the idea is that we try to extract the solution from the graph, and if we succeed, then we return that as the plan. Otherwise, we check whether no solution possible in the graph, and when can we say that? If we have already reached the fixed point, right, then we will say that no solution possible in the graph, then return failure. Otherwise, we expand the graph to one more level. An expansion of the graph means that you take the set of current set of literals and use the set of actions to deduce the next set of literals, right. So, this is the GraphPLAN algorithm. So, it is a variant of iterative deepening, which you can see is that we are expanding one level at a time, then checking whether we have the goals in non-mutex way, and if so, then we try to extract the solution. Otherwise, we expand another level of the graph, right. Now, what does this extract solution do? It tries to work backwards from the set of goal propositions which we have achieved in the last level of the graph to determine that which is the set of independent actions which were able to produce these literals, right. So, I start with the set of goal propositions. So, suppose I have goal proposition G1 and I have goal proposition G2, and I have them in the last level of the graph in non-mutex fashion. So, I try to figure out that which are the set of actions. So, there can be many actions which have achieved this, right. Now, I look at these actions and then I have to find out a pair of non-mutex actions which are able to achieve this. Now, see that there can be more than one non-mutex actions pairs that achieve this, right. Now, which pair will eventually succeed all the way backwards, we do not know. Suppose I pick this action and this action, right, then this action has some preconditions. So, suppose this action has preconditions L1 and L2 and this has preconditions not of L1 and L3, right, or it still has L1 and L3, but then L2 and L3 are mutex, right. So, in this way you will have to work backward and be able to determine the plan, right. So, there is a search involved in this also, right. Now, what I want you to do is to figure out that how this search will work, right, how will extract solution graph work, and then I want you to create an example where I have the goal propositions in a non-mutex way here, but the planning graph unfolded so far does not have a solution, right. This is the same exercise that I was talking about previously. What I want you to do is to figure out that suppose I have the goal literals in a mutex way, non-mutex way, and I want to figure out whether there exists a plan in the graph that I have unfolded so far, right. So, try to think of an algorithm for doing this. That is part 1. Read the book Russell Norvig or any other book which has this planning algorithm, and try to figure out that what will be the algorithm of extracting this plan out of the unfolded state, unfolded plan graph, right. Then if you can figure that out properly, then you will also understand how to create an example where the planning graph that you have so far still does not have a plan. It still does not have a plan, but the goal propositions are appearing in a non-mutex way, right. See, this is very important to understand, because that is going to determine the complexity of the algorithm. So, you cannot stop the moment you find that the goal propositions have appeared in a non-mutex way. That is not sufficient for stopping the planning algorithm. You may still have to unfold a few more levels.
So, at each step I apply all the actions.
You apply all the actions.
So
You
when we were unfolding the graph, then at a particular state if we found some actions mutex, then accordingly in the next level we decided that these actions are also mutex depending upon the conditions or pre actions.
yes.
So
yes.
won't be able to reduce for the goals also. We are going at each step we are deciding for the next action.
Yes, the problem is we are taking it pairwise. We are just looking at it pairwise, not set wise. We are not considering subsets of actions which are which are independent. We are just looking at pairs, right. So, this is just a hint that where the problem lies, but I want you to figure it out. I want you to look at some examples, try to work it out in your mind. But the main problem here is that we are just looking at pairs of actions which are incompatible. Just try to think whether transitivity will hold in this inconsistency relation. If A and B are consistent, B and C are consistent, then are A and C consistent? If A and B are inconsistent, if B and C are inconsistent, then can A and C ever be consistent? Right. Try to answer these questions, then you will get a flavor of what you need to do. Right. Okay. Right. So the termination of GraphPLAN depends on a set of things. Firstly is literals increase monotonically. So once a literal has arrived in the plan, it will always be there, right, because the persistence actions will ensure that they will always be there, right. So new actions can bring in new literals, but this cannot happen forever because the set of literals is finite. Actions increase monotonically. Some action which was not applicable because the set of literals did not contain its precondition can later on become applicable because those preconditions have now come into, those literals have now come into the new state. So therefore new actions can become applicable. But again the set of actions that we have is finite. So again that also cannot happen forever. And the third thing is that mutexes decrease monotonically. So something which is currently non-mutex can never become mutex later on, right. So these are the 3 points which ensure that the GraphPLAN algorithm will terminate. Right. Now I am in a peculiar problem because I do not have time to clean up SATPlan within the remaining time. So let us do this. We will address SATPlan in the next lecture. And any questions on this GraphPLAN? Yes.
So the mutex link between the propositions, the literals, is it dependent on the actions through which they are obtained? So like as in the example shows that G1, G2.
Yes. Yes.
Then the G1, G2, if the precondition L1, L2, L3 are mutually exclusive.
L2, L3 are mutually exclusive, then these two actions will also be
Mutually exclusive. Does that make G1 and G2 mutually exclusive?
Yes, it does. Provided that, no, it could be that you are, that G1 and G2 is non-mutex because there might be another pair of actions which make them non-mutex. See, if you have any pair of non-mutex actions which are able to achieve this, then the mutex link will not be there, right. So my suggestion is that read through this algorithm in the book, right, and then try to figure out that how we are going to extract the solution from a partial planning graph. Yes.
Then we are not applying persistence rule to each and every vector. How do you decide to which should we apply?
You have to apply it on everyone, on all. On all literals,
possible actions at every
yes, yes. For all literals and their negations, literals means that the propositions and their negations, you will have to have the persistence actions for them, for all of them, right. So that actually represents the fact that you can carry over these to the next time step, but new things will also come. Well, people actually devised this algorithm for several reasons. One was that we were at that point of time in the early 90s, new data structures were coming up which made this fixed point computation quite convenient. So, there is a branch of calculus called mu calculus. This mu calculus talks about computations in terms of fixed points and tells you that what kind of things that you can compute and what you cannot, right. So, I am not going to go into the details of this, but then there was a data structure called a binary decision diagram. Are you familiar with binary decision diagrams? No, binary decision diagrams. Which are alternatively called BDDs. Well, BDDs are a kind of representation of the of Boolean functions. So, they are canonical and they are reasonably compact also, not for all functions, but from a given a binary decision diagrams, once you construct the BDD, then you can solve the SAT and the unsat problems just by traversing the BDD, so traversing a path in the BDD, right. So, one subject that came up was that whether we could use these BDDs for fixed point computations, right, and from an entirely different problem, there came up the notion of symbolic computation with these BDDs. Right. So, what do these BDDs do? So, suppose we have a set of states, right, and a set of states can be represented in binary. Each state can have a binary encoding, right, fixed length binary encoding. Then a set of states is nothing but a Boolean function which is true if you present it with one of the valid states and is false for others, right. Any Boolean function can be thought of as a representation of a set which contains the valid minterms and does not contain the minterms which do not belong to that function. So, it is a set of minterms. So, any Boolean set of items which can be encoded in Boolean in binary strings. So, that can be represented by a logic function. Is that clear? Yes or no? Right. So, what we can do is we can start with an initial set of states and we can have a BDD for that initial set of states. So, this is our S0, right, and suppose we have a set of actions A. So, what does A do? A checks whether the precondition of every action is there in S0, and if so, then the post condition of A gets added to this BDD. So, what happens is S1 is actually some Boolean function of S0 and A. Now, what this A is? This A is another BDD which has present state next state pairs, right. So, it has present state next state pairs. So, if your present state is in the BDD, then your precondition is satisfied and then the next state is what is going to get produced, right. So, what we can do is we can produce S1, which is basically the set of states which are reachable by one action from S0. Now, which action? So, this A is the set of all actions. So, what we will have in S1 is the set of all states that are reachable from S0 by applying any of these actions, right. So, what we do is we take not only this, but take the union of this with S0. So, this is our S1. Then our S2 is f of S1 with A union with S1, right, and we continue to do this until we find that for some step Sk is equal to Sk plus 1, right. Now, what BDDs help us in doing is it helps us doing these computations quite easily, and the advantage of using this is that we are applying all the actions with a single Boolean operation. So, when we are doing this FS0A, it is one single BDD operation which is going to have the effect of applying all the actions on the given state and to produce the entire collection of next states that this set of actions can produce, and the BDD will be a compact representation for this next set of states, right. So, this is why now in more recent times people have attempted to solve the GraphPLAN kind of problems with these kind of data structures, right. And more recently people found out that symbolic computation with BDDs has certain problems, like the BDD sizes can combinatorially explode for large number of variables. On the other hand, Boolean satisfiability is something which people have studied from ages. Boolean satisfiability or CNF satisfiability is something which people have studied for nearly 6-7 decades now, if not more. So, therefore, the kind of solvers that we have for solving SAT problems are very rich. So, what people found out is that rather than representing the Boolean functions as BDDs, if you just represent them as a set of clauses, then the existing SAT solvers are able to solve the problem much more quickly than you can do with BDDs, and the space requirement is much lesser, right. So, the SATPlan algorithm attempts to harness the power of the currently available SAT solvers. In the next lecture we will talk about SATPlan. So, in the last lecture we had studied the algorithm GraphPLAN, and today we will see that with slight modifications to the style in which GraphPLAN works, we can convert the planning problem into a Boolean satisfiability problem and solve it using SAT solvers. The reason why people wanted to why SATPlan was born was that there were a lot of new SAT solvers which could handle very large satisfiability problem instances and could solve them very quickly. So, to harness the power of this kind of SAT solvers, we can actually translate problems into SAT problems and solve them with SAT solvers, which was previously not practical because of the inherent complexity of SAT. So, the inherent complexity of SAT is still the same, it is still NP complete, but what people have found out is that many problems, many instances can be solved very efficiently, and in practice the instances which are very hard to solve do not appear very commonly.
Move A on top of it directly.
No, this means move B to top of A.
Yes, sir.
Yes.
In that case, not possible to do move B comma A, sir.
Because it is already on top.
Yes, sir. In that case also, sir.
No, in that case it can be true also, there is no problem. you can just pick it up and put it down back there, right. No, but the condition that, see, I think you are confused. What you are saying is what we have written here. This says move B to top of A, right. So, right. So, we have just written what you are saying is exactly what we have written here. So, you have A on top of B, so you cannot move B to top of A. That is what you wanted to say, right. Okay, so in addition to this, there will be a bunch of other things also, like we will have action exclusion axioms. Now, this basically tells us which actions are mutex. So, for example, you can let me write down one action exclusion axiom. So, I have move B A and now let us see what this says. This says move B to the top of A and in the same time step move B to table, right. So, it is the extract solution part which is hard, right. The one that we totally glossed over is actually the hard problem, right. Once you have the set of goal propositions in non-mutex form, then extracting the solution is hard, right. So, because that is hard, so if your problem is NP complete in nature, then that part is really difficult to solve, right. So, algorithms like GraphPLAN and SATPlan, which solve them as satisfiability problems, tend to work better for NP complete kind of problems.